Hey everyone, welcome back. Today, we're going to be doing a bit of a deep dive into something pretty technical, but trust me, it's super fascinating stuff. We're talking about how to make large language models run faster, way faster. You probably used LLMs before. Think chatbots, text generators, all of that good stuff. But have you ever stopped to think about just how much computational power is behind those seemingly simple interactions?
Yeah, it's pretty mind-boggling if you really think about the sheer scale of these models. I mean, we're talking billions, even trillions of parameters that need to be processed for every single word or phrase that these things generate. It's really no wonder that efficiency is like a major concern for developers working in this space.
Exactly. And that's exactly why we're diving into this awesome guide from NVIDIA's developer blog today. It's like a playbook for all the tricks and techniques that developers are using to squeeze every ounce of performance out of LLMs. And honestly, I mean, nobody wants to wait an hour for an LLM to write a simple poem or
Right. Absolutely. Latency is a killer when it comes to user experience, especially in interactive applications. So let's get into the nitty-gritty of how these optimizations actually work.
Okay, let's unpack this. So first, we need to understand like where the bottleneck actually lies in LLM inference. So expert speaker, can you walk us through the basics of how LLMs work at a technical level?
Sure. So at the heart of most modern LLMs is what's called the transformer architecture. And transformers rely heavily on a mechanism called attention, which allows the model to weigh the importance of different parts of the input when it's generating the output. And this process happens in two main phases: prefill and decode.
Okay, so prefill and decode. What exactly happens in each of these phases?
Okay, so in the prefill phase, the LLM takes the input text, let's say your prompt, and it breaks it down into tokens. Think of these as the individual words or subwords that the model understands. Then it converts these tokens into numerical representations called embeddings. And these embeddings capture the meaning and context of the words. From these embeddings, the model calculates keys and values, which are essential for the attention mechanism. So essentially, the prefill phase sets the stage for the model to generate text based on your input.
Got it. So the prefill phase is all about setting the context, like getting the LLM ready to generate the output. What about the decode phase? That's where the actual text generation happens, right?
Exactly. The decode phase is where the magic happens, but it's also where the main bottleneck lies. Unlike the prefill phase, which can be highly parallelized, the decode phase generates text token by token, sequentially. Each new token is generated based on the previously generated tokens and the information stored in the key value cache from the prefill stage. This process is inherently sequential because the model needs to maintain coherence and consistency in the generated text.
So it's like building a house brick by brick. You need each brick in place before you can lay the next one.
Precisely. And each time the LLM generates a new token, it needs to access all those previously calculated keys and values, which are stored in the KV cache. This constant back and forth between the model's parameters and the KV cache is what creates the memory bottleneck.
Okay, yeah, I'm starting to see the problem here. We've got this massive model, potentially billions of parameters, and then this ever-growing KV cache that needs to be accessed for every single token generation. No wonder things can slow down.
Exactly. It's not just about raw processing power, it's about memory bandwidth and access speed. Even if your GPU has tons of processing cores, it's constantly waiting for the memory to deliver the data it needs. This is what we call a memory-bound problem.
Okay, so it sounds like the key to speeding up LLM inference lies in finding ways to manage this memory bottleneck effectively. Like, we need to make sure the LLM can access the information it needs as quickly as possible.
Absolutely. And that's where the real fun begins. This NVIDIA guide really dives deep into a whole arsenal of techniques for optimizing both the model itself and the way it's deployed, all with the goal of maximizing memory efficiency and minimizing latency.
Okay, I'm ready to dive into this arsenal. But before we get to the specific techniques, can you break down what consumes the most memory during LLM inference? Like, what are the biggest culprits?
So there are two primary memory hogs: the model weights themselves and the key value cache, which we've already touched on. The model weights represent the learned knowledge of the LLM, essentially the billions of parameters that define how it processes information. These weights can take up a massive amount of memory, especially for larger models.
Okay, so the model weights are like the LLM's brain, and the bigger the brain, the more memory it takes up. What about the KV cache? How big can that get?
The KV cache can actually become even larger than the model weights themselves, especially for long input sequences and large batch sizes. Think about it. The KV cache stores the context for all the previously generated tokens. And as the sequence length grows, so does the cache. Plus, if you're processing multiple requests simultaneously in a batch, the cache needs to store the context for all of those requests as well.
Wow, so the KV cache is like this ever-expanding memory bank that can quickly overwhelm the system if not managed carefully. It sounds like finding ways to optimize this cache is crucial for improving LM inference speed.
Absolutely. And that's just one piece of the puzzle. There are several other techniques, from model parallelism to attention optimization and even shrinking the model itself, that play a crucial role in making LLMs run faster and more efficiently. But we'll dive deeper into those in the next part of our deep dive.
Okay, I am definitely hooked. We've got a lot more ground to cover, so let's take a quick break and come back to explore these fascinating techniques in detail. All right, so we're back and ready to really get into these techniques that can help us overcome this memory bottleneck in LM inference. Expert speaker, you mentioned something called model parallelism earlier. What exactly is that and how does it help?
Yeah, so model parallelism is this really powerful technique for distributing the computational load of an LLM across multiple GPUs. So like instead of trying to fit the entire model onto a single GPU, which can quickly hit memory limits, we can split the model into smaller chunks and let different GPUs handle different parts of the computation.
Okay, so it's kind of like dividing and conquering the LLM, right? Each GPU gets a piece of the action. But how do we actually decide how to split the model? I imagine there are different ways to do that.
Yeah, you're right. The NVIDIA guide outlines like three main approaches to model parallelism: pipeline parallelism, tensor parallelism, and sequence parallelism. You can think of them as different strategies for like dividing up the work and assigning it to different GPUs.
Okay, so I'm visualizing three different slicing techniques for our LLM cake here. Let's start with pipeline parallelism. How does that work?
Okay, so pipeline parallelism is like an assembly line for LLMs. So imagine each GPU as a station on the assembly line, responsible for processing a specific set of layers in the model. The data flows through the pipeline, with each GPU doing its part and passing the results on to the next one.
Okay, so instead of one GPU struggling to handle the entire model, we create this chain of GPUs, each specializing in a certain stage of the process. That sounds pretty
Yeah.
efficient.
It can be very efficient for large models, especially for reducing the memory footprint on each individual GPU. However, there's a potential drawback: pipeline bubbles.
Pipeline bubbles, that doesn't sound good. What are those?
So think about like a real assembly line, right? If one station is slower than the others, it can create a bottleneck. It causes delays and backups. In pipeline parallelism, a similar thing can happen. If one GPU is slower than the others, it can create a bubble in the pipeline where other GPUs are left idle, waiting for the slower one to catch up.
So it's like a traffic jam on our LLM assembly line. Yeah. That makes sense. So pipeline parallelism is great for distributing the load, but we need to be mindful of these potential bottlenecks. What
Okay.
about tensor parallelism? How does that differ from the pipeline approach?
So instead of dividing the work by layers, as in pipeline parallelism, tensor parallelism splits the data within each layer across multiple GPUs. Imagine you have a giant matrix representing the weights of a particular layer. In tensor parallelism, we slice this matrix horizontally, like cutting a pizza, and distribute the slices to different GPUs.
So each GPU gets a portion of the data for each layer, rather than being responsible for a specific set of layers. Interesting. When would this approach be more advantageous than pipeline parallelism?
Tensor parallelism is particularly useful for layers that involve very large matrix multiplications, which are common in LLMs. By distributing the matrix across multiple GPUs, we can parallelize these operations and significantly reduce the computation time.
Okay, so it's all about choosing the right strategy based on the specific computational needs of each layer. What about the last one, sequence parallelism? How does that fit into the picture?
So sequence parallelism takes a different approach altogether. Remember how the input text is broken down into tokens? Well, in sequence parallelism, we exploit the fact that certain operations can be performed independently on different parts of the sequence. So we split the sequence across multiple GPUs and let them work on their assigned chunks in parallel.
So instead of dividing the model itself, we're dividing the input data and processing it in parallel. Clever.
Yeah.
What kinds of operations are well suited for this approach?
So operations like layer normalization and dropout, which are common in transformer models, can be performed independently on different parts of the sequence without affecting the overall computation. By parallelizing these operations, we can reduce the memory footprint and speed up the processing.
All right, so we've got these three powerful tools for model parallelism: pipeline, tensor, and sequence. It sounds like developers can mix and match these techniques to find the optimal configuration for their specific model and hardware setup.
Exactly. It's like a toolbox for scaling LLMs. You can choose the tools that best fit the job. And you can even combine them in creative ways to achieve even higher levels of performance.
Okay, this is fascinating. So we've gone from understanding the memory bottleneck to exploring ways to distribute the model itself across multiple GPUs. But it sounds like there's even more to the story, right? We can also optimize the attention mechanism itself.
Absolutely. The attention mechanism is at the heart of transformer models, and it's also a major contributor to the memory bottleneck. But there are some very clever techniques for making it more efficient. We'll dive into those next.
Okay, I'm ready for more attention-grabbing insights. Let's hear it. Welcome back to our deep dive into the world of LLM inference optimization. We've explored model parallelism and attention optimization, and now it's time to uncover even more techniques for boosting those LLM speeds. Expert speaker, where do we go from here?
So we've been focusing on optimizing how the LLM processes information, but what about the information itself? What if we could make the model smaller, more compact without sacrificing its performance? That's where model slimming comes in.
Model slimming. Sounds
Yeah.
intriguing. It's like we've been building a bigger house for our LLM, but now we're realizing that maybe we can live just as comfortably in a more efficient, minimalist space.
Exactly. The NVIDIA guide outlines 3 key techniques for achieving this model slimming: quantization, sparsity, and distillation. Each of these techniques targets different aspects of the model, but the goal is the same: reduce the memory footprint without compromising accuracy.
All right, let's break these down one by one. Let's start with quantization. What exactly does that involve?
Okay, so think about a high-resolution image, right? It might look beautiful, but it also takes up a lot of storage space. You could compress that image by reducing the number of colors or the level of detail. You might lose a bit of fidelity, but the overall picture would still be recognizable. Quantization does something similar for LLMs. It reduces the precision of the numerical values used to represent the model's weights and activations.
So instead of using very precise high-resolution numbers, we switch to slightly lower resolution ones. Does that really make a significant difference in terms of memory?
Oh, it can make a huge difference. Instead of storing each value as a 32-bit floating point number, we might use only 16 bits or even 8 bits. This can significantly reduce the memory footprint of the model, allowing it to fit into smaller GPUs or run faster on existing hardware.
That's amazing. But I'm curious, does reducing the precision of these values affect the accuracy of the LLM? Do we lose any intelligence in the process?
That's the key challenge with quantization, finding the right balance between compression and accuracy. Fortunately, LLMs are surprisingly robust to quantization. In many cases, we can reduce the precision of the weights and activations quite significantly without a noticeable drop in performance.
That's great to hear. It sounds like quantization is a relatively straightforward way to shrink the model without losing too much intelligence.
Sure.
What about sparsity? How does that work?
Sparsity takes advantage of the fact that many of the values in an LLM are very close to zero. And these near zero values often don't contribute significantly to the model's output. It's like having a giant library with lots of empty shelves. We can save a lot of space by simply removing those empty shelves.
But we're basically trimming the fat, getting rid of all those unnecessary values that are just taking up space without adding much value.
Exactly. In practice, this involves representing these near zero values as actual zeros, which allows us to store and process the model more efficiently. There are different techniques for achieving this sparsity, some involving pruning away unimportant connections in the model, while others use specialized data structures to store only the non-zero values.
Okay, so we've got quantization for reducing the precision of the values and sparsity for removing the unimportant ones. What about distillation? That sounds like a completely different approach.
Yeah, distillation is a fascinating technique that involves training a smaller student model to mimic the behavior of a larger, more complex teacher model. It's like having a master craftsman pass on their skills and knowledge to an apprentice. The student model learns from the teacher model, essentially inheriting its intelligence in a more compact form.
So we're creating a mini-me version of the LLM, a more efficient version that can run on less powerful hardware without sacrificing too much performance. That sounds incredibly useful.
It can be very effective, but there are some challenges. Distillation requires careful training and tuning to ensure that the student model learns effectively from the teacher model. Plus, as we discussed earlier, licensing restrictions on many LLMs can make distillation tricky. You can't just go around creating student versions of any model you want.
Right. There are legal and ethical considerations to keep in mind. But overall, it sounds like these model slimming techniques, quantization, sparsity, and distillation, offer powerful ways to reduce the memory footprint of LLMs without compromising their intelligence. It's like we've unlocked a whole new level of efficiency.
Absolutely. And remember, all of these techniques are constantly evolving and improving. Researchers are constantly developing new methods for making LLMs smaller, faster, and more efficient.
This has been an incredible journey. We've gone from understanding the memory bottleneck to exploring a whole range of techniques for overcoming it. Model parallelism, attention optimization, clever caching, and now model slimming. It's amazing to see the ingenuity and creativity that's going into making LLMs more accessible and practical for real-world applications.
Yeah, it's a truly exciting time to be working in this field.
Mm.
The pace of innovation is incredible, and who knows what the future holds for LLM inference optimization. We might see even more radical approaches like analog computing or entirely new hardware architectures designed specifically for these massive models.
It feels like we're just scratching the surface of what's possible with LLMs. And to our listeners, if you're eager to learn more, I highly recommend checking out the NVIDIA blog post we've been discussing. It's a fantastic resource for anyone who wants to delve deeper into this exciting field. And who knows, maybe you'll be the one to come up with the next breakthrough in LLM inference optimization. Until next time, keep those brains buzzing and happy learning.